Today we shall continue the queuing problems that we are discussing in our previous class. So, in this context, let us see the problem that we have taken in our previous class, that is what we said, that in a service center only one person can get service, any other arriving customer has to wait outside as there is no place available. The customers arrive randomly at 8 per hour, service is exponential and it's 6 minutes on the average. Find the probability that an arriving customer will have to wait outside, right. So, what is basically said? Basically said, it is here that this is the queue, in fact there is no queue space, right. So, this is the service, but the queue space is outside. It is not that there is no queue space, the system is still the entire thing. This is the queuing system. This is the queuing system and this is the queue, but this queue space is outside. That means the people are waiting outside and there is a single place where there is no place to wait, and this is where the service counter is, right, and this is where the arrival customer and this is where the service customer. So, what we have to find here, right, what we have to find here is that an arriving customer will have to wait outside. That means, what is the probability that the person is in service, and it should be 1 minus that. Is it okay? So, is it like a busy period, right? It is like a busy period. So, let us look at that, how this busy period is coming to be equal to, right. So, average arrival rate is lambda is 8 per hour, average service rate is 6 minutes since mu is 10 per hour. So, utilization factor rho is lambda by mu, that is 8 by 10 equal to 4 by 5. So, what is the probability that there is nobody in the system, that is P 0, that is 1 minus rho and 1 by 5. So, if the system is empty, there is nobody in the system, so a person who arrives will immediately get the place free and get into the service. What is that probability? That probability is nothing but P 0, that is equal to 1 by 5. So, there is a 20% chance that the person will find the place free, and since there is no place to wait, right, an arriving customer has to wait outside when there is no place free inside. So, the probability that an arriving customer has to wait outside is equal to 1 minus probability that the arrival finds the place free equal to 4 by 5 is 80%, and this 4 by 5 is same as the 4 by 5, that is the utilization factor rho. Sometimes it is also called the busy period, is it not? Because what, let us see that once again, that rho is equal to utilization factor, and 1 minus rho is the P 0, that means probability that nobody in the system. Please remember, all the discussions we are doing here, they all pertain to MM1, right. So, that is P 0. So, probability that nobody in the system. So, what is the probability of system busy or server busy equal to 1 minus P 0 equal to 1 minus rho equal to rho. So, utilization period factor in case of MM1Q is also an indicator of busy period. So, in the problem that we have done, we have got 80% as the utilization factor. So, 80% is the busy period, and since there is no place to sit, it is also imperative that the people have to wait outside will be 80%. But is it all the time this exact same formula is true? That means the probability of the system that is server busy is equal to a person have to wait outside. It may not be so. Look at this another problem. In this problem, one person can get service and another one can wait. That means it is like a barber shop with one chair, isn't it? Something like that. So, any other arriving customer has to wait outside as there is only one place available inside. The customer arrives randomly at 8 per hour. The service is exponential and again 6 minutes on the average. Find the probability that an arriving customer will have to wait outside. Look here, in this case it is not simply P0, that should be excluded. Suppose even if there is one customer in the system, right, and then he is busy, another arriving customer can still get a chair, right. So, what should be the probability? What should be the probability that the system is free, right? Then there is nobody in the system or there is one person in the system. If there is nobody in the system, you go directly to the service. If there is one person in the system, he must be in the service. So, go and get the chair. Only if there are more than two people, only if there are two persons in the system, then you have to wait outside, or two or more. Is it all right? So, what is that probability? That probability for the second case, right. So, the first case what we have done, that is no facility for waiting. Now, in the second case, one facility for waiting, that is the second case. So, in the second case, what is happening? P0 probability that nobody in the system, P1 is the probability that one person in the system. This is the probability that an arriving customer will get to go inside. So, what is the probability to wait outside? Is 1 minus B0 minus B, right. So, that should be the probability to wait outside. So, here it is given that since the row is 4 by 5, we have already seen, probability that arrival will find the place free is P0 plus P1, because either you can get the service or you can wait inside, and that is equal to 1 by 5 plus 4 by 25 equal to 9 by 25, right. So, an arriving customer has to wait outside when there is no place free inside. So, probability that an arriving customer has to wait outside becomes 1 minus 9 by 25 equal to 16 by 25 or 64%. So, you see what has happened? The probability of waiting outside has reduced from 80% to 64% with just giving one facility, right. Let us take another problem, but this problem is one of uniform distribution, right. In case of uniform distribution, what really happens is that the things are not random. In a random facility, what is usually happening is that the probabilities are according to a certain distribution, right, that is Poisson distribution or exponential distribution if you take the inter-arrival time. But in this case is a much simpler probability problem where we simply assume an uniform distribution. Let us look at the problem. In a suburban station, trains arrive regularly every 30 minutes beginning 6:30 am in the morning. A man who does not know the train timings arrive randomly, uniformly distributed between 7:40 am and 8:15 am every morning. Right? So, what is the probability the man has to wait for more than 10 minutes for a train? Is it all right? So, here it is a very simple analysis, but really we have to understand this very clearly. So, it is like 7:40, the person can come between 7:40 and 8:15. So, this is 7:40, this is 8:15. So, if I draw a continuum, then this is how the thing is. Somewhere here is 8 o'clock and this is where the train is arriving. See, the person can come any time between 7:40 to 8:15. Suppose he comes at 7:40, he has to wait for more than 10 minutes. Suppose he come at 7:50. So, let us say somewhere here. So, this is 7:50. If he comes at 7:51 and a little more than 7:50, then he has to wait less than 10 minutes. Is it all right? But if he comes after 8, that means train is gone, the next train is at 8:30, right. This is where this is the next train, is the another train that is at 8:30, because every half an hour there is a train. So, he has to wait because he comes by 8:15. So, he has to wait all this time anyway. Now, moment he is gone, the train, obviously he has to wait. That means, this is the time and this is the time. These are the time when if he comes, then he has to wait more than 10 minutes. How much time is this? This is 10 minutes, this is 15 minutes. But if he comes by 7:50 plus, then obviously he has to wait less than 10 minutes. So, probability of waiting more than 10 minutes equal to 10 plus 15 divided by 35 equal to 25 by 35 to 5 by 7, right. So, probability of waiting more than 10 minutes would come out to be 25 by 35 equal to 5 by 7. So, look at this, the man has to wait more than 10 minutes, that is P0 x between 0 to 10 and x between 20 and 35. So, x is a uniform random variable between 0 to 30. So, desired probability will be 5 by 7. Is it all right? So, that is the problem on uniform distribution. Now, a very important question that we had discussed so many times, but still I thought that this point has to be focused one more time. Show that if the number of arrivals of customer to a facility follows the Poisson distribution, then the inter-arrival time of the customers to the facility follows the exponential distribution, right. Now, how can we show this? Maybe we can take an example. So, what happens? We find out a result from Poisson distribution point of view, and again we find the same result from exponential distribution point of view, and see that both the results are similar, right. So, let us see some of the distribution values. So, it is indeed true that number of arrivals of customer to a facility follows the Poisson distribution, then the inter-arrival time between the customers will follow the exponential distribution. So, Poisson distribution, which is an discrete distribution, the probability mass function equal to Px is equal to lambda t to the power x e to the power minus lambda t by factorial x, right. And if you really sum it, then you get the CDF or cumulative distribution function CDF fx will be sum of n equal to 0 to infinity, then lambda t to the power n e to the power minus lambda t by factorial n. On the other side, for exponential distribution, probability density function fx equal to lambda e to the power minus lambda x, right. And cumulative distribution function, because become fx equal to 1 minus e to the power minus lambda x, right. So, these are the results which are going to be useful to us for this understanding. Now, let us take a particular example, right. So, if we take a particular example, that is first of all what we need to do, let us take an example, they say lambda equal to 2 per hour, and let us take a time of 1 hour duration. So, what is lambda t? Lambda t will be 2 into 1 equal to 2. Now, what is the probability? Suppose we are really asking what is the probability of no arrival within 1 hour. Probability of no arrival within 1 hour. So, P none. What is P none? We need to calculate from both sides, right, or sometimes it might simply call it as P0 also, that nobody arrives. So, what is P0? Now, look at this probability mass function is lambda t to the power this thing. So, let us put here probability of x equal to 0 and lambda t equal to 2. So, from this equation we get P0 equal to, what is lambda t? Lambda t equal to 2, x equal to 0, e to the power minus 2 by factorial 0. 2 to the power, this is become 1. So, this becomes e to the power minus 2, right. So, this is what we get from the your Poisson distribution. Similarly, suppose we use this one, please also remember that these fx is nothing but Px less than equal to 1. So, that means what will be the probability that nobody will arrive, right. So, we need to find out probability of no arrival from here P0, that will become 1 minus e to the power minus 2, right, that also becomes e to the power minus 2, right. So, must remember that when we have to find out the probability of no arrival, then this is the cumulative density function. That means the inter-arrival time is between 0 to 1, right. That is what, if you want to find out, then you have to find out this formula, I mean within the given time. And if we want to find out that none arrives within this given time, that will become 1 minus of this function. So, that will be 1 minus of e minus 2 equal to e minus 2. So, both the figures are similar, and look at the slide, similar thing is also described there, that for Poisson distribution we find probability of no arrival P 0 equal to e to the power minus 2 is 13.5%, and from exponential distribution it is P x greater than 1, which is 1 minus P x less than equal to 1, right. That means this is the thing that we shall get actually the particular function, the cumulative density function. So, this we can do, and we can get e to the power minus 2 equal to 0.135 is 13.5%, right. So, this is what we can get. Now, another very important property which we have discussed earlier also, which is known as the memoryless property. And why it is called memoryless? Let us understand this once again. Say suppose let us look at an example first before we look at those equations. If suppose in a parking lot on a Sunday, the last arrival was at 12 noon, right, 12 noon. Now, so lambda is 1 per hour, inter arrival time is exponential, nobody has arrived till 1 p.m. What is the probability that nobody arrives before 2 p.m.? You see, this problem is like there is the last arrival was at 12 noon, up to 1 p.m. nobody has come. What is the probability that nobody arrives before 2 p.m.? So, you tend to think that if you start thinking from 12, then what is the probability that nobody arrives in 2 p.m. given that nobody have arrived by 1 o'clock, is it all right. So, maybe you tend to calculate this particular thing, that is a conditional probability of x greater than 2 given that x is greater than 1, is it all right. But already we have seen that probability of something. So, here itself let us we can do this side. So, supposing what is the probability of x greater than 2 given that x is greater than 1, is it all right. So, it is like a conditional probability. So, what is the probability of x greater than 2? This is nothing but e to the power minus 2. So, already we have seen what is the probability of x greater than 1, and there it was lambda is 2, here lambda is equal to 1, right. So, lambda t is also 1 if t equal to 1, and lambda t equal to 2 if t equal to 2. This is t equal to 2, right. So, this will be therefore e to the power minus 2 by e to the power minus 1. So, it will now come to nothing but e to the power minus 1. But if you would have directly calculated that it is like nobody has arrived till 1 p.m. So, simply start the time from there and not at 12 p.m. right. So, 1 p.m. is the start of time. What is the probability that next arrival will be by 2 p.m.? It is nothing but probability of x greater than 1, right. Nobody arrives by 2 p.m. So, it is nothing but e to the power minus 1 because lambda t equal to 1. So, this value is same as this value, is it all right. So, this is exactly what happens, that if someone has already waited delta t minutes, then probability that the person waits another t minutes is the same as that of someone else who is going to wait t minutes from the beginning. Supposing you are playing a game of dice, right, and you will win if you get a 6. You have it's assume that it's a perfect Markovian process, and it's an unbiased die, and casting has absolutely no issue. So, supposing you have already played 5 times and you have not got a 6. What is your probability of getting a 6 time? You may be thinking, no, it is almost certain. But in reality, it is exactly same as someone who is casting the die for the first time. Is it all right? There will be no difference at all, right? So, if you look at this memory, lack of memory, p x greater than t plus delta t, given that x is greater than delta t, it is a conditional probability, is nothing but p x greater than t, is all right. So, LHS is e to the power minus lambda t plus delta t by e to the power minus lambda delta t, it comes out to be e to the power minus lambda t, right. So, this is precisely what is known as the memoryless property. So, if we already know that nobody has come by 1 p.m., we can easily calculate those things from there, and we need not really worry about the other things. So, here is an example. In a parking lot on a Sunday, last arrival was at 12 noon, arrival rate was 1 per hour, service rate was mu equal to 2 per hour, number of arrivals is Poisson and inter arrival time is exponential. So, service time is also exponential. So, what is the probability that next arrival is before 1 p.m., right? What is the probability that next arrival is between 1 and 2 p.m.? What is the probability that next arrival is after 2 p.m.? And last one, if nobody arrived till 1 p.m., what is the probability of next arrival before 2 p.m.? In all these questions, what we really have to understand is, that in the first case, what is the probability that next arrival is before 1 p.m., right? So, in this case lambda equal to 1, t is also 1, right. So, it should be lambda t equal to 1. So, how much it should be? The probability will be, what is the probability that the arrival will be beyond 1 p.m.? It will be e to the power minus 1. So, it will be the reverse of that. So, let us look at this, that lambda equal to 1, t equal to 1. So, lambda t equal to 1, and therefore, required probability will be 1 minus e to the power minus lambda t is 1 minus e to the power minus 1. In the second case, what is the probability that next arrival is between 1 and 2 p.m.? So, it is the probability of arrival before 2 p.m. minus probability of arrival before 1 p.m. So, that already we have seen for 1 p.m. 1 minus E1. So, before 2 1 minus e to the power minus 2. So, the first one minus the second one. What is the probability that next arrival after 2 p.m.? It will be e to the power minus 2, already we have seen it. And nobody arrived till 1 p.m. Probability that next arrival is before 2 p.m. Again we can use memoryless property, and it should be 1 minus e to the power minus 1. Let us look at some of the service side also. Server is serving at 1 p.m. Probability that it is not complete by 2 p.m. not complete by 1:10 p.m. right, and not complete by the last one, we wrote wrongly, that is okay, the same figure is taken, but let us ignore the third part. Let us look at the first two. So, what is the probability that server is serving at 1 p.m. probability that it is not complete by 2 p.m. right. So, mu equal to 2 hours using memoryless property t equal to 1 hour. So, required probability is e to the power minus 2 star 1 is e to the power minus 2, and second case the t is 1/6 hour. So, it should be e to the power minus 1 by 3, right. So, these are the some of the problems that we can really work out, and in the next class we shall continue to see certain other systems other than MM1, right. So, thank you very much.